Chapter 8 Electron Configuration and the Chemical Periodicity. In this chapter, we'll study characteristics of many electron atoms, the quantum mechanical model and the periodic table, trends in 3 atomic properties, and the chemical reactivity. In studying hydrogen atom, we learned that there are 3 quantum numbers: principal quantum number N, angular momentum quantum number L, and the magnetic quantum number M. These quantum numbers describe the energy, shape, and orientation of an atomic orbital. It turns out that there's a 4th quantum number, spin quantum number, that becomes more important when we describe many electron systems. This quantum number was discovered by the following experiment. When a beam of atoms such as silver or hydrogen atom pass through a non-uniform magnetic field, it splits into 2 beams. So before the magnetic field, they travel in one direction, and after magnetic field, they becomes 2 directions. So that indicates that the interaction of these atoms with the magnetic field is quantized. There are 2 ways for them to interact with the magnetic field. So here is the explanation of this observation. The electron of an atom spins on its axis along 2 opposing directions. One is clockwise, one is counterclockwise. We learned in physics that a spinning charge generates a magnetic field whose direction depends on the spin direction. So here we have electron spin in opposing directions. This generates magnetic field with opposing directions. And therefore, when these atoms pass through magnetic field, they split into 2 traveling directions. The spin directions of this clockwise, counterclockwise are specified by the spin quantum number ms. Okay, one is a positive half, one is negative half. So the conclusion is that each electron in an atom is described completely by 4 quantum numbers. The first 3 describe the orbital, while the 4th quantum number, which is ms, describes electron spin. Here's a summary of quantum numbers of electrons in atoms. Principal quantum number, angular momentum quantum number, magnetic quantum number describe the orbital energy, orbital shape, orbital orientation. And the 4th quantum number, spin quantum number, which have 2 values, positive half, negative half, describes the direction of electron spin. In addition to the 4th quantum number, spin quantum number, there are other features become more important when we discuss many electron systems. So one of them is called the Pauli exclusion principle. And this principle states that no 2 electrons in the same atom can have the same 4 quantum numbers. Okay, so let's assume you have 2 electrons. They have same N, L, and M. Okay, note that N, L, M describe the orbital. So if 2 electrons has same N, L, M, they are in the same orbital. For example, 1s orbital. Okay, so in this case, N is 1, L is 0, that's s orbital, and M can only be 0, so 1 orientation. So that's 1s, only 1 orbital. Now, if 2 electrons in the same orbital with the same L, N, L, M, according to Pauli exclusion principle, the 4th quantum number cannot be the same. Okay, because you cannot have 2 electrons same 4 quantum numbers. If 3 are the same, the fourth one cannot be the same. So one must be half, the other negative half. Okay, so if we can use a square to represent the orbital, we have 2 electrons, one half, let's say, is spin up, the other is spin down. Okay, so 2 spin directions. Now, is it possible we can put another electron? Well, because only 2 possible the spin quantum number, so if we put the third one, then it either either up or down. So if we put inside the orbital, then these two has the same 4 quantum numbers, N, L, M, and Ms, and therefore that's against the Pauli exclusion principle. So there's no way we can put the third electron into the orbital, and that leads to the conclusion that an atomic orbital can hold a maximum of 2 electrons, and they must have opposing spins, spin up, spin down. And when an orbital have s orbital has 2 electrons, spin up, spin down, we say these electrons are paired. In studying hydrogen atom, we learned that the energy of hydrogen atom is determined by the principal quantum number only. So one equation to calculate energy is negative a constant, which is 13.6 electron volts divided by n squared. N is the principal quantum number. So if electron in 2s orbital or 2p orbital, they will have the same energy because they have the same principal quantum number, even though the angular momentum quantum number are different. So here L equals 0 and here L equals 1, but they have same energy because they have the same principal quantum number. Now for many electron systems, however, the energies of atomic orbitals are affected by nuclear charge, shielding effect, orbital shape. And this leads to the conclusion that energy for many electron systems not only determined by principal quantum number but also by angular momentum quantum number. And therefore 2s orbital, 2p orbital, they have different energy because they have different angular momentum quantum number. 2s orbital has energy lower than 2p orbital. A higher nuclear charge increases nucleus-electron interactions and lowers sublevel energy. Let's compare an electron in 1s orbital in hydrogen, so here hydrogen, in helium ion, and in lithium 2+ ion. It takes about 1,311 kilojoule per mole energy to remove an electron in 1s orbital from hydrogen. On the other hand, it takes about 5 times the energy to remove electron from 1s orbital from helium. Okay, so greater nuclear charge lowers the sublevel energy. It takes more energy and to remove 1s electron from helium ion than from hydrogen. Similarly, in lithium 2+, the nuclear charge increase, and therefore it takes even higher energy. So here is 11,815 kilojoule per mole to remove the electron from 1s orbital. In many electron systems, each electron is not only attracted by the nucleus, but also repelled by other electrons. Repulsions counteract nuclear attraction somewhat. In effect, repulsions due to other electrons partially share the nuclear charge and reduce it to a smaller value called effective nuclear charge. Let's take a helium atom as an example. In helium atom, there are 2 protons and 2 electrons. For convenience, let's label them A and B. Electron B is not only attracted by the two protons, but also repelled by electron A. So in effect, electron A partially shared the nuclear charge. So electron B experiences a nuclear charge less than 2. In this case, it's about 1.7. And this is called effective nuclear charge. In helium ion, on the other hand, there's only one electron. And so this electron experiences the full nuclear charge, 2+. To remove this electron from the helium ion, it takes 5,250 kJ per mole. To remove electron B from helium atom, it only takes 2,372 because electron A shared the nuclear charge. So this shielding effect reduces the full nuclear charge to an effective nuclear charge of 1.7, and that makes electron B easier to remove. In lithium atom, there are 3 protons and 3 electrons. 2 electrons are in 1s orbital and 1 electron in 2s orbital. These 2 electrons in 1s orbital partially shared the nuclear charge, so the electron in 2s orbital experience an effective nuclear charge only 1.3. And this is a big change from 3+ to 1.3. Okay? Electrons in an inner level, which refers to the electron in 1s orbital, has a larger shielding effect than the electrons in the same level as in helium atom. So compared with lithium 2+, there's only one electron, and this electron experiences a full nuclear charge 3+. And to remove this electron from the ion, it takes 2,954 kJ per mole energy. To remove electron from 2s orbital in lithium atom, it only takes 520 kJ per mole. So again, the inner shell electron 1s orbital, the 2 electrons, has a larger shielding effect than the electrons at the same level. Orbital shape also affects energy. Let's look at radial probability distribution for 2s orbital and the 2p orbital. So 2p orbital has a maximum, okay, closer to the nucleus than 2s orbital. So in general, in average, the electron in 2p orbital is closer to the nucleus than 2s orbital. However, 2s orbital also has a small maximum here that even closer to the nucleus. And therefore, electron in 2s orbital can penetrate closer to the nucleus. And this penetration increases the nuclear attraction of the 2s orbital and decrease shielding effect. And the consequence is that the energy of 2s orbital is lower than 2p orbital. So in general, the orbital of a lower L value is smaller than the energy of orbital with higher L value. From our discussion above, we can see that each energy level is split into sublevels of different energy. Splitting is caused by penetration and its effect on shielding. For a given n value, a lower L value indicates a lower energy sublevel. Order of sublevels are: energy of s orbital is lower than p orbital, and the energy of p orbital is lower than d orbital, and the d orbital has a lower energy than f orbital. In general, the principal quantum number n is the main factor to determine energy. So the orbital with n equals 1 is lower in energy than those orbitals when n equals 2, which are lower in energy than those orbitals with n equals 3. So 1s orbital is lower in energy than 2s and 2p, which are lower in energy than 3s and 3p. And as L increase, energy also increase. So when n equals 2, 2p is greater than in energy than 2s orbital. And when n equals 3, 3p orbital is higher in energy than 3s orbital. Now, as n increase, some sublevels overlap. So here are the orbitals when n equals 3. So n equals 3, 3s, 3p, 3d. And here are the orbitals when n equals 4. Okay, so you can see 4s orbital is actually lower in energy than 3d orbital. And similarly, 5s orbital is lower in energy than 4d orbital. Now, knowing this order of the energy levels is very important when we write electronic configurations. So if we have a many electron system, the electron first go to lowest energy level, and that's 1s orbital. And if we have more electrons, it will go to 2s orbital, and then 2p orbital, and then 3s orbital, 3p orbital, 4s orbital, 3d orbital, 4p orbital, 5s, 4d, 5p, 6s, and so on. Electron configuration is a shorthand notation consists of the principal energy level N value, the letter designated of sublevel L value, and the number of electrons in the sublevel. So for hydrogen atom, for example, so hydrogen has 1 electron. So the electron is the lowest energy level, which is n equals 1, the first energy level. And when n equals 1, L can only be 0, which we call s orbital. And for L equals 0, m can only be 0, so 1 orientation. So to write electron configuration, we write n, L, and the number of electrons. N is 1, L is s, so 1s, and the number of electrons is 1, so put here, so 1s1. Okay, that's the electron configuration for hydrogen atom. An orbital diagram consists of a box, okay, or just a line. So we write a box to represent the 1s orbital for hydrogen atom, or just a line, okay? And then we put an arrow, okay, with an arrow representing each electron and its spin. Because hydrogen has 4 quantum numbers, okay, n equals 1, L equals 0, m equals 0, the spin quantum number can be half or negative half. Because when you have 1 electron, so ms can be written as half. And we write arrow, so it's spin up, okay, to represent m equals half. All right, so 1 spin means 1 electron spin up. Or we write here, okay, on the line to show we have 1 electron spin up, ms equals half. Let's look at the orbital diagram for helium atom. So we already know the energy order. 1s orbital is lower in energy than 2s orbital, okay, because n equals 1, here n equals 2. And when n equals 2, 2s is lower than 2p, because here L equals 0, L equals 1. And when L equals 1, we have 3 orientations. So here is px, py, pz. They are 3 orientations, but they all have same n and L, and therefore they have same energy. Okay, so we put them side by side, means they have same energy. Now, helium atom has total of 2 electrons. How do we feel the energy orbitals? Okay, well, the 2 electrons go to 1s orbital, lowest energy level. And according to Pauli exclusion principle, no 2 electrons can have exactly same 4 quantum numbers. So for 1s orbital, n equals 1, L equals 0, m equals 0. So the 2 electron has same quantum number n, l, m. So the spin quantum number cannot be the same. One must be spin up, one must be spin down. So here is the orbital diagram for helium. 2 electrons, both in the 1s orbital, one spin up, one spin down. When building orbital diagrams, we use alphabet principle and the exclusion principles. The alphabet principle says that electrons are always placed in the lowest energy sublevel available and then build up from low energy level to higher energy level. So for hydrogen atom, we only have one electron, and this electron goes to the lowest energy level, and that's 1s orbital with a spin up. And the exclusion principle states that each orbital may contain a maximum of 2 electrons, which must have opposite spin. Helium has 2 electrons, so both can go to the same energy level, the lowest one, which is 1s orbital, and they are spin up, spin down. How about the lithium atom? Well, lithium atom have 3 electrons. According to alphabet principle, we start with lowest energy level 1s orbital. And according to Pauli exclusion principle, this energy orbital can only hold 2 electrons. So maximum 2 electrons, spin up, spin down. And the third one must go to the higher energy level, 2s orbital, with the spin up. So here is the orbital diagram for lithium. And note that we can also draw energy diagram horizontally. So we have a square 1s orbital with a spin up, spin down, 2 electrons, and then 2s orbital with only 1 electron spin up. So that's also orbital energy diagram for lithium. Now the electron configuration you can write as 1s orbital has 2 electrons, and then 2s orbital has 1 electron. Let's draw orbital diagrams for beryllium and boron. Beryllium have 4 protons and 4 electrons. You can find this information from periodic table. So 2 electrons goes to the lowest energy level, 1s orbital, and 2 goes to the higher energy level, 2s orbital. And therefore, the electron configuration is 1s2, 2s2, and the orbital diagram we can also draw horizontally. So that's 1s, 2 electrons, and 2s, 2 electrons, spin up, spin down. Now, what about boron? So boron have 5 electrons, and so we have 1 more electron, and the higher energy level than 2s is 2p. We have 3 of them. Okay, they are all equivalent, different orientation. So the 5th electron should go to any of those. And by convention, we start with the left one. Okay, so the electron configuration should be 2s2, 1s2, 2s2, 2p1. And the orbital diagram should be 1s, 2 electrons, 2s, 2 electrons, and the 2p, the left side has 1 electron spin up. Let's now draw orbital diagram of carbon. Carbon has 6 electrons, so electron configuration start with 1s, 2 electrons, 2s, 2 electrons, and the 2p, 2 electrons. Remember, 2p has 3 equivalent orbitals. So how does the orbital diagram look like? Well, here are the orbitals. So 1s has 2 electrons, 2s has 2 electrons, and 2p has 3 equivalent orbitals. So we put 1 electron in the first orbital, and this adds together is 5. And carbon has 6. So where does the 6th electron go? According to Hund's rule, when orbitals of equal energy, so these orbitals, 3 of the 2p orbitals are equal energy. Okay, when these equal energy orbitals are available, the lowest energy electron configuration has the maximum number of unpaired electrons. So the 6th electron, if we put in the left orbital with the 5th electron, according to Pauli exclusion principle, one orbital can hold maximum 2 electrons with opposing spin. That means the 6th electron must be spin down, and that means the 2 electrons are paired. Okay, that's against the Hund's rule. Hund's rule says it has maximum number of unpaired electrons, and therefore the last electron cannot go to the same orbital as 5th electron. It has to go to a different orbital, either here or here. Okay, by convention we go to the second one, and this Hund's rule also says the electrons must be parallel spin. Parallel spin means the last one has the same spin as the 5th one, and so it must also spin up. Okay, so the correct orbital diagram should look like this. Okay, so we have a 2p orbital, so 3 of them, 2 of them are occupied by 2 parallel spin, both up. Let's draw orbital diagram for nitrogen. Now nitrogen has 7 electrons, so the electron configuration should be 1s 2 electron, and then 2s 2 electron, and then 2p 3 electrons. So it has 1 more electron than carbon, and we already know the energy orbital diagram for carbon looks like this. So 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and according to Hund's rule, 2 electrons must be in 2 different 2p orbitals with a parallel spin. Okay, now nitrogen has 1 more electron, so where does the electron go? Again, according to Hund's rule, it needs to have maximum unpaired electron with a parallel spin, so the last one must go to the 3rd 2p orbital. Okay, so that goes to here, so that it has maximum unpaired electron with a parallel spin. So this is nitrogen orbital diagram. What about next one, oxygen? So oxygen, the Z will be 8 electrons. So electron configuration should be 1s2, 2s2, 2p4. And so after filling these 3 orbitals with maximum unpaired electron, with parallel spin, so now you have 1 more electron. So this electron has to go to one of these 3 orbitals. So by convention, we go to the first one. And according to Pauli exclusion principle, it has to have opposite spin, and so spin down. So this is oxygen orbital diagram. And then fluorine will be, so fluorine will be 9, and electron configuration 2p has to have 5 electrons. And so the next one goes to the 2nd 2p orbital, again with opposite spin. And then last one will be neon, which has 10 electrons. So the last electron goes to the 3rd 2p orbital with opposing spin, opposite spin. So that fills all the orbitals till the n equals 2, all the way to n equals 2 orbitals. Sample problem 8.1. Write a set of quantum numbers for the 3rd electron and a set for the 8th electron of the fluorine atom. So we need to identify the electron of interest and note its n, l, m, ms, 4 quantum numbers. Count the electrons in the order in which they are placed in the diagram. Fluorine has 9 electrons. Electron configuration is 1s2, 2s2, 2p5. The energy orbital diagram, let's draw it. So this is a 1s orbital, 2s orbital, and 2p3 equivalent orbitals. Okay, so we start with one s orbital, so 2 electrons. First one, second one, and the third one goes to 2s orbital. So it asks us about third electron. That's the one. Okay, so that's the third electron, and then fourth electron pair, okay, spin down, and the fifth one goes to the left 2p orbital. So this is the fifth one, and then according to Hund's rule, the sixth one goes to the next orbital, parallel spin. That's the seventh one, and the eighth one goes to the first one, spin down. So that's the eighth electron, is right here. Okay, and then ninth one goes to here. So this is the orbital diagram of fluorine. So now let's answer the question. Again, here is the orbital diagram, and the third one is right here, this orbital, and it asks about the quantum numbers. And because it's 2s orbital, so the principal quantum number is 2, and s means L equals 0. Okay, and when L equals 0, m has to be 0. So only one orientation. So it's spherical. All right, and spin up. Okay, when spin up means the spin quantum number is positive half. So here are the 4 quantum numbers: n equals 2, L equals 0, m equals 0, and the spin quantum number is positive half. Now the 8th one is right here, as we shown in this diagram. So this is 8th one, and the principal quantum number is again number 2. Okay, n equals 2, and the p orbital is L equals 1. When L equals 1, m can be 0, can be -1, can be +1. According to our convention, the first one is -1. So this is -1, and this is 0, and this is +1. So because this 8th electron in the first orbital, so m should be -1. And because its spin goes down, so it's -half. So here are the 4 quantum numbers: 2, L equals 1, m equals -1, and the spin quantum number is -half because it's spin down. Here shows electron configurations for the first 10 elements. So the first one is hydrogen with 1 electron in 1s orbital, so 1s1. Helium 2 electrons, so 1s2. And up to this point, n equals 1 is 4. So the first orbital, 1s orbital, can only hold 2 electrons. And when n equals 1, there's only 1 orbital, 1s orbital. Lithium is the beginning of the second shell, n equals 2. And it starts to fill the 2s orbital, okay, 2s1, beryllium 2s2. Okay, boron now has an actual electron goes to 2p orbital, so it starts to fill 2p orbital. So 2p1 for boron, 2p2 for carbon, 2p3 for nitrogen, 2p4 for oxygen, 5 for fluorine, and 6 for neon. So up to this point, n equals 2 is 4. Okay, so this shows that elements in the same group has a similar auto shell electron configuration. For example, hydrogen 1s, 1 electron. Lithium auto shell 2s, 1 electron. So 2s1, 1s1. So auto shell electron configuration are similar. And if we look at helium and the neon, so helium has 4 auto shell electron, 1s2. And for neon, 2s2, 2p6 also 4 in the auto shell electron. The elements with similar auto shell electron configuration tend to have similar chemical properties. So helium, neon are both very stable, and they usually don't form compounds. Sometimes it's more convenient to draw a partial orbital diagram, which shows only the highest energy sublevels being filled. Let's take aluminum as an example. Aluminum has 13 electrons. So the electron configuration is 1s2, 2s2, 2p6. Remember, up to this point, second shell is 4. So n equals 2 is 4. And this is exactly the neon electron configuration. Aluminum has more electrons, 3 more electrons. So the electrons goes to the next shell, which is 3s2 and then 3p1. So the 3s, 3p are the 2 orbitals of the highest energy sublevels. In fact, these are the electrons in these orbitals determines the chemical properties. So that's the one we are interested in. And we draw partial orbital diagram only show these 2 orbitals, 3s 2 electrons, 3p 1 electron. Ignore the inner shell electrons. A condensed electron configuration has the element symbol of the previous noble gas in square brackets. So we already know the inner shell electron configuration is actually the configuration of neon, and therefore we can simplify the electron configuration of aluminum as this one. Okay, bracket neon. So this represents 1s2, 2s2, 2p6. Okay, so the second shell is 4, and that's the electron configuration for neon. And then 3 electrons goes to 3p2, 3p1, and 3s2, 3p1. So this symbol represents condensed configuration of aluminum. Here shows the condensed electron configurations in the first 3 periods. So hydrogen, again, 1s, 1 electron, helium, 1s, 2 electrons. So the first shell is 4. Lithium start to fill the second shell. Okay, so we use helium bracket to represent the electron configuration for the first shell. Okay, it's 4, and then the extra electron goes to 2s, 1 electron. All right, beryllium, helium electron configuration, followed by 2s2, boron, 2s2, 2p1, carbon, 2s2, 2p2, 2s2, 2p3 for nitrogen, 2s2, 2p4 for oxygen, 2s2, 2p5 for fluorine, and the neon, 2s2, 2p6. So the second shell is 4. Sodium start to fill the third shell. So neon brackets indicates that the second shell is 4. So this electron configuration of inner shell electrons. And extra electron goes to 3s orbital, so 3s1, and magnesium 3s2, aluminum 3s2, 3p1, and then 3s2, 3p2, 3s3, p3, until argon 3s2, 3p6. Again, n equals 3 is 4. So we can see again the auto shell electron configuration is the same for the same group elements. And you can see hydrogen 1s1, lithium 2s1, sodium 3s1. Okay, so let's look at the oxygen 2s2, 2p6, sulfur 3s2, 3p4. So 2s2, 2p4 for oxygen, 3s2, 3p4 for sulfur. And let's look at the neon. Okay, 2s2, 2p6, 3s2, 3p6. So for elements in the same group, they have same auto shell electron configuration, and therefore they have similar chemical properties. Here shows the partial orbital diagrams and the electron configurations for the elements in period 3. Start with sodium, 11 electrons. And the 4 electron configuration is 1s2, 2s2, 2p6, 3s1. So 3s1 is the highest energy level orbital, and these are the inner shell, which has electron configuration of neon. So the condensed electron configuration is a bracket, neon bracket, and then 3s1, okay, to only show this highest energy sublevel orbital. And partial orbital diagram, we only show 3s, 3p. So 3s only have one electron, so that's sodium. And then magnesium has one more electron, so this both goes to 3s2, 3s electrons. Okay, so again, condensed configuration is neon, 3s2 electrons. And aluminum has one more electron, goes to 3p. Okay, silicon, 2 electrons go to 3p. According to Hund's rule, they should be a different orbital with parallel spin. Okay, and then phosphorus, okay, you have 3 electrons in 3 different 3p orbitals. Okay, until argon. So all the p orbitals are 4. And so the condensed electron configuration is a bracket, neon bracket, to show the inner shell is 4 and the outer shell is 3s2 electrons, 3p6 electrons. In summary, period 3 starts with sodium and alkaline metal that has one more electron than neon. The electron goes to 3s orbital. Magnesium and alkaline earth metal has 2 more electrons. Both go to 3s orbital. From aluminum to argon, 6 elements fill 3p orbital. Okay, so these two 3s, so s orbital has 2 electrons, and the p has 3 orbitals. Okay, px, py, pz. So altogether 6 electrons. So here 6, here 2. Now when n equals 3, L can be 2. So this is L equals 0 for s orbital. L equals 1, L equals 2 when n equals 3. And L equals 2, that's d orbital. So for the third shell, we have d orbital. And for d orbital, there are 5 orientations. So that means 5 orbitals. 5 orbitals can hold 10 electrons. Okay, so the next element is 19, which is potassium, another alkaline metal. And potassium has one more electron than argon. The question is, does this electron go to d orbital, 3d? Okay, the answer is no, because the 3d orbital is effectively shielded from the nuclear charge by inner shell electrons. Furthermore, 4s orbital penetrates closer to the nucleus. So it turns out that 4s orbital is actually lower in energy than 3d orbital. So the next period, period 4, starts with 4s instead of 3d. Period 4 starts with potassium, another alkaline metal which has 19 electrons. The 4 electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. Now up to this point, this is the electron configuration of argon. Now we know that for third energy level, there's also a d orbital, so 3d orbital. However, as we explained before, 3d orbital actually has energy higher than 4s orbital. So potassium, the extra electron goes to 4s orbital. And next one, calcium, another alkaline earth metal, 2 electrons goes to 4s orbital. So from potassium to calcium, 4s orbital is 4. So the next one, scandium, 1 more electron start to fill d orbital. Now remember, d orbital has 5 of them. Each of them can hold 2 electrons, so that's 10 electrons. From scandium to zinc, 10 elements fill the d orbitals. So 3d that has 10 electrons. Okay, now these elements in general has electron configuration 4s2, 3d 1 to 10. Okay, this is because up to Cassian here, 4s orbital is already 4, and that's why from scandium to zinc, in general, 4s should be 2 electrons, and then the actual electron go to d until d becomes 10. However, there are 2 exceptions. Okay, one is chromium, one is copper. So these 2 has electron configuration 4s1. Okay, we'll explain these 2 later. Now up to zinc, so d orbital is 4. So the next one, gallium, the actual electron goes to p orbitals, 4p orbitals. And we have 3 4p orbitals that can hold 6 electrons. So gallium until krypton, p orbital is 4. Okay, so krypton is another inert gas with electron configuration, argon electron configuration, and then 4s2, 3d10, and 4p6. Let's look at the 2 exceptions, but first let's look at vanadium. Vanadium has 23 electrons, and the electron configuration starts with argon configuration, and 5 more electrons go to 4s orbital, and then 3d. So 3 electrons in 3d orbital. So the next one is chromium, 24 electrons, and you would expect the actual electron just go to 3d orbital. So the electron configuration would be 4s2, 3d4. Now it turns out that half field and field sublevels are unexpectedly stable or low in energy. So for chromium, it is possible to achieve half field in 3d orbital by moving 1 electron from 4s to 3d. This way, okay, the electron configuration becomes 4s1, 3d5. So 4s1 becomes half field. 3d also becomes half field because 3d can hold 10 electrons and now 5. So both becomes half field, and that is very stable. Okay, so this is the correct electron configuration for chromium, 4s1, 3d5 instead of 4s2, 3d4. Now the other exception is copper, which has 29 electrons. The element before it is nickel, okay, which has 28 electrons, and the electron configuration start with argon 4s2, 3d8. So you would expect it has configuration for copper should be 4s2, 3d9. Now it is possible to achieve 4 level in d by moving electron from s to d orbital, and so the correct one is 4s1 and 3d10. So that's the electron configuration for copper. Reading the periodic table from left to right gives the energy order of levels and sublevels. So the periodic table starts from 1s orbital, and then 2s orbital, followed by 2p orbital, and next 3s, 3p. Before it goes to 3d, it starts with 4s, and then 3d, and then 4p. Next, before 4d, it goes to 5s first, and then 4d, 5p, and again, before go to 4f, it goes to 6s, and then 4f, and then 5d, and 6p. So the elements with d electrons are called d block. Okay, electrons of p orbitals are p block, and this is s block, okay, and f block. Here's another way to show the order of the energy levels of different orbitals. So first, write the principal quantum number vertically, 1, 2, 3, 4, 5, 6, 7, and then draw all the orbitals for each principal quantum number. So for example, here is 2s, 2p, and here 3s, 3p, 3d, 4s, 4p, 4d, 4f, and so on. And then draw diagonally arrows so that m plus l is constant. So for example, let's look at this direction. So 3p principal quantum number is 3, l is 1, so add together is 4. 4s principal quantum number is 4, and l is 0, add together is 4. So in this direction, the n plus l are both 4. Okay, so this way we can easily show the order of the orbital energy levels of orbitals. So you start with 1s, and then 2s, and then, okay, according to the arrow, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and then 4d, 5p, 6s, followed by 4f, 5d, 4p, 7s, and so on. Electrons can be classified as inner or core electrons and autoelectrons. Autoelectrons are those in the highest energy level or highest n value, and the inner or core electrons are those electrons inside autoelectrons. Now, it is these autoelectrons that determines the properties, chemical or physical properties of the elements. So these autoelectrons usually are very important, and they are called valence electrons, particularly for main group elements. For transition metal elements, they also have d orbitals. So these d orbitals also participate in chemical reactions, and therefore they are also counted as valence electrons. For example, the first transition metal, scandium, the electron configuration is 4s2 and 3d1. So these adds together are the valence electrons. I want to mention that if d or f orbitals are 4, then they usually do not contribute to the reactivity, so they are not counted as valence electrons. For example, technetium, the electron configuration krypton 5s2, 4d10, and 5p4. So note that the d orbital is 4, 10 electrons. So these are not counted as valence electrons. So for technetium, the valence electrons are 2 of the s orbital, 4 of the p orbital, and that's 6 valence electrons. Here shows the periodic table, and group 1, group 2, these are s block because the auto-electron configuration contains s orbital. So for example, hydrogen is 1s1 and beryllium 2s1 or 2s2. Okay, so they are ns1 to 2. So they are s block, and these elements, okay, they are p block because the auto-electron configuration is ns2 mp6 1 to 6. So for example, let's see, chlorine is 3s2 3p5. Okay, so these are p block, and both S block and the P block adds together are called main group elements. Okay, here is called the transition elements with D block. These elements contains d orbitals, electrons, d electrons, and between here, okay, are elements called inner transition elements or F block, and these elements contains F electrons. Now it is important to notice that elements in the same group has similar auto-electron configuration. For example, sodium 3s1, potassium 4s1, rubidium 5s1. So group 1, they all have electron configuration ns1. And beryllium 2s2, magnesium 3s2, calcium 4s2. So they all have ns2. Another example is the last group, okay, inert gases. Neon 2s2, 2p6, argon 3s2, 3p6, krypton 4s2, 4p6. Elements in the same group of periodic table have the same auto-electron configuration. Elements in the same group of periodic table exhibit similar chemical behavior. Similar auto-electron configuration correlate with similar chemical behavior. Group 1 elements, alkali metals from lithium to sodium to potassium, rubidium, they all have similar chemical reactivities. For example, they can react with water and displace hydrogen gas. Group 7, called halogens, from fluorine to chlorine to bromine to iodine, they also have similar properties. For example, they can react with metals to form ionic halides. For example, sodium with chlorine forms sodium chloride, the table salt. Sodium react with bromine to form sodium bromide. Sample problem 8.2. Using the periodic table on the inside cover of the text, give the full and the condensed electron configurations, partial orbital diagram showing valence electrons only, and the number of inner electrons for the following elements. So our plan is we look at the periodic table, find the atomic number. Atomic number gives the number of protons and therefore the electrons also. And then from periodic table, we also know the order of filling orbitals. The partial orbital diagram includes all electrons added after the previous noble gas, except those in filled inner sublevels. Let's look at A, potassium. So here is a periodic table. It's a simplified version. And we find potassium right here, atomic number 19, so 19 electrons. To write the full electron configuration, okay, we look at the periodic table. So start from hydrogen to helium, that's 1s, 2 electrons. Lithium to beryllium, 2s, 2 electrons. Beryllium to neon, 2p, 6 electrons. Sodium to magnesium, 3s, 2. Aluminum to argon, 3p6. And potassium has one more electron, which goes to 4s, 1 electron. All right, so the full configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. The condensed configuration, we choose the previous noble gas, which is argon. Okay, so we write argon, okay, brackets, and then 4s1. To draw the orbital diagram, we show only the fourth row, which has one 4s orbital, 5 3d orbital right here, and 4p orbital, okay, right here. But only one electron to fill this row or this period. So it's in 4s orbital, one electron. Okay, so that's a partial orbital diagram. Now, how many inner shell electron, core electrons? Well, this is outer shell. Outer shell only have one electron, so inner shell should have 18 electrons. Let's look at B, technetium. So again, in this periodic table, we find the technetium right here, atomic number 43. So the electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, so 4s2 from potassium to Ca, and then 3d10, all right, and then here is 4p6, and then start to fill fifth of the row. Here is 5s2, and then this 4d, so 4d, 1, 2, 3, 4, 5 electrons. So the 4 electron configuration as shown here, okay, until 4d 5 electrons. Now to draw the condensed configuration, we use the previous noble gas, which is krypton. Okay, so bracket krypton, which has electron configuration until 4p6, and then the fifth row we have 5s2, 4d5. Now to draw the orbital diagram, we only show the fifth row, so the 5s orbital. Okay, so this is the 5s, 4d, and 5p. Okay, now 5p is empty. 5s has 2 electrons, and 4d has 5 electrons. Okay, so that's partial orbital diagram. Now, how many auto electrons? Now, auto shell electron is 2, so 2 plus 5 is 7, and therefore the inner shell 43 minus 7, so that's 36 inner electrons. Let's look at C, lead. So in periodic table, we find lead right here. So it's atomic number 82. So we write electron configuration according to the periodic table. So here from hydrogen to helium, that's 1s2. From lithium to beryllium, 2s2. And then boron to neon, 2p6. 3s2, here 3p6, 4s2, 3d10, here 4p6, and then fifth row 5s2. Okay, these are 4d, so 4d10, 5p6, and then sixth row 6s2. Okay, note that there's an insertion here for the inner transition metals from lanthanum to ytterbium. So that's 14 electrons. So 14, these are F of block. So F, so that's 4f14, and then goes to 5d10. So this is 5d10, and then 4p. So 4p. This is 4p1, and lead is 4p2. Okay, so that's 4 electron configuration. Now the condensed configuration, we write the previous noble gas. So the previous noble gas is xenon. So right here, xenon electron configuration until 5p. Okay, and then so we write bracket xenon, and then followed by 6s2, 4s14, 5d10, and 6p2. To draw the partial orbital diagram for valence electron, we note that the f orbital is 4. Okay, f can hold 14 electrons. If it's 4, it shouldn't be counted as the valence electron. Same as the d orbital, it's 10d orbital. D 10 electron is 4, and therefore we only have a valence electron 6s2, 6p2. So that's 4 electrons. So 6s 1 orbital with 2 electrons, 6p 3 electrons. P has 3 orbitals, and we have 2 electrons. So Hund's rule says they should go to different orbitals with a parallel spin. So we already draw the 4 electron configuration, condensed configuration, and a partial orbital diagram to show the valence electrons. We have 4 valence electrons, and the rest should be the inner electrons. This includes the electrons represented by xenon, which is 54 electrons, plus 14 of in f orbitals, 4 f orbitals, and 10 electrons in 5d orbitals. So that's added together give you 78 inner electrons. Some atomic properties are directly influenced by electron configuration and the effective nuclear charge. These properties are periodic, which means they generally exhibit consistent changes or trends within a group or period. One example is atomic size. If we look at the periodic table, you can see for main group elements, atomic size increase down a group, from top to bottom, the atomic size increase, and the decrease across a period. So from left to right, the atomic size decrease. And here are the reasons. As we move down a main group, the principal quantum number increase. Each member has one more level of inner electrons. For example, lithium electron configuration 1s2, 2s2. So the inner electrons are these 2 electrons in 1s orbital. For sodium, on the other hand, is 1s2, 2s2, 2p6, 3s2. So these are the inner electrons. So compared with lithium, sodium has one more level. The second level is 4. Okay, and these inner electrons can shield the outer electrons very effectively. And the probability that the outer electrons will be further from the nucleus increases, and consequently, the atoms get larger as a result of the increasing n values. Across a period from left to right, the effective nuclear charge increase. For example, lithium has 3 protons, beryllium has 4, boron has 5. So from left to right, the number of protons increase, and therefore the nuclear charge increase. Although number of electrons also increase from left to right. These electrons are added to the same outer level, in this case, the second level. And the shielding by inner electrons does not change. And therefore, the increase of number of protons outweigh the increase of number of electrons, and the effective nuclear charge increase from left to right. So due to this increase of effective nuclear charge, the outer electrons are pulled closer to the nucleus, and therefore the atomic size decrease from left to right. Sample problem 8.3. Using only the periodic table, rank each set of main group elements in order of decreasing atomic size. So we need to locate each element on the periodic table. And remember, main group elements increase in size down a group and decrease in size across the period. A, calcium, magnesium, strontium. So here is a periodic table, and we find calcium right here, magnesium, and strontium. So these are the elements in second group, and we know the size increase down a group. So strontium should be the largest. Next will be calcium, and the magnesium should be smallest. Okay, next one, potassium, gallium, calcium. So potassium is here, gallium is here, and the calcium is here. So these are three elements in a row or period. So across period, the size decrease, and therefore potassium is the largest, and then calcium, and then gallium. C, bromine, rubidium, krypton. So we find these three elements in the periodic table, and bromine is here, krypton is here, rubidium is here. Okay, now it's convenient if we compare them with the potassium, because down the group rubidium is greater than potassium. So down group size increase, rubidium is greater than potassium. Across a period, the size decrease. So from left to right, potassium is the largest, then bromine, then krypton. Okay, so from this we can see rubidium is the largest, and the second is bromine, and the third is krypton. Okay, now let's erase this. So next one, we need to find the strontium. So strontium is here, calcium here, and the rubidium here. So let's see. Down the group, size increase. So strontium should be greater than calcium. Now across period, size decrease. So rubidium should be greater. So rubidium should be greater than strontium, and therefore we have the size. Rubidium is the largest, strontium is the second, calcium is the smallest. Here again shows the periodicity of atomic radius. So atomic radius as a function of atomic number. The first element is hydrogen right here, and then helium. So this is period 1, and you can see the size decrease from hydrogen to helium. Same for period 2, lithium, beryllium. Here is boron, carbon, and then nitrogen, oxygen, fluorine until neon. So that's a period 2, and you can see across period the size decrease. And here period 3, sodium, magnesium. Okay, so magnesium, and then aluminum, silicon, phosphorus, sulfur, chlorine until argon. Okay, same is for period 4, period 5. So you can see in general the size decrease. Okay, decrease across a period. Now, if we look at down a group, so this is group 1, lithium, sodium, potassium, rubidium. So here group 1, and down a group, the size increase. And so for all the groups increase, and this is group 8. And so helium, neon, argon, krypton, xenon. So the size increase down a group. In addition to atomic size, ionization energy also changes periodically. Ionization energy is the energy required for the complete removal of 1 mole of electrons from 1 mole of gas atoms or ions. Atoms with a low ionization energy tend to form cations. For example, sodium, by removing an electron, it forms sodium cation. So the energy to remove this electron is the ionization energy. The smaller the ionization energy, the easier for this process to proceed. So atoms with low ionization energy usually are metals, so they can form cations easily. Now, atoms with a high ionization energy tend to form anions. For example, chlorine, to remove electron from chlorine forms chlorine cation needs a lot of energy. So usually this doesn't happen. Instead, chlorine gain electron to form chlorine anion. Okay, so a atom like a chlorine with high ionization energy usually go this way to form anions, except noble gas, because noble gases are very stable. So it takes a lot of energy to remove electron. So these noble gases have high ionization energy, but they are stable, and so they usually don't form either cations or anions. Ionization energy tend to decrease down a group. So we already know in a periodic table, in the same group, down a group, the size increase. So atomic size increase. So when atomic size increase, the auto electron is further away from nucleus, and therefore it's easier to remove them. And that means you need a smaller ionization energy. So go down a group, as the atomic size increase, the ionization energy decrease. Now across a period, we know the diameter becomes smaller, the size becomes smaller. When the size becomes smaller, the electrons becomes more attracted to the nucleus, and so it takes more energy to remove them, and therefore the ionization energy actually increase across period. So that's why across the period from left to right, it goes from metal to non-metal. The ionization energy increase, the atomic size decrease. This diagram shows the periodicity of the first ionization energy. Let's compare with atomic size. As we already explained, down a group, atomic size increase. So let's look at the first group, lithium, sodium, potassium, rubidium, cesium. So atomic size increase down a group. Now let's look at the ionization energy, lithium, sodium, potassium, rubidium, cesium. So ionization energy decrease down a group. Now let's look at across the period. So the atomic size should decrease. Let's look at period 4. So from potassium to krypton, you can see atomic size decrease, and ionization energy from potassium to krypton, the ionization energy increase. And so the trend of ionization energy is opposite to the trend of atomic size. This diagram shows the first ionization energies of the main group elements. Again, the trend is clear, and let's compare with atomic size. So down a group, size increase, and down a group, ionization energy decrease. The trend is opposite. Across period, the size becomes smaller, and across period, the ionization energy increase. Let's look at two exceptions. According to the trend, ionization energy increase from left to right, but boron has ionization energy 800, less than beryllium 899. And let's look at the partial orbital diagram. For beryllium, 2 electrons in the 2s orbital, and that's beryllium. So boron, you have 2 electrons in the 2s orbital and 1 electron in the 2p orbital. So this is 2p. So remember, half field orbital or 4 orbital are more stable. So by removing this electron from 2p orbital, boron becomes an ion with a 4 orbital with 4 electrons, and therefore it's easier to remove this electron, because the resulting ion is more stable. So that's why the ionization energy for boron is actually smaller than beryllium. Similarly, if we look at the ionization of the orbital diagram for nitrogen and oxygen, so nitrogen is 2s2 and 2p. So 2p you have 3, so 1, 2, 3. So that's nitrogen. And the oxygen has one more electron, so put the electron here in the first orbital here. And you can see again, by removing this electron, you get a half-filled orbitals. So these are 2p orbitals. Becomes half-filled, and that's stable. And therefore, it's easier to remove that extra electron from oxygen. And the ionization energy of oxygen is actually smaller than nitrogen. Sample problem 8.4. Using the periodic table only, rank the elements in each of the following sets in order of decreasing the first ionization energy. So first we need to find these elements in periodic table. And remember, the first ionization energy generally decrease down a group and increase across a period. A. Krypton, helium, argon. So in periodic table, krypton is here, helium is here, and argon is here. So these elements are in the same group. And we know down group, the atomic size increase, ionization energy decrease. And therefore, krypton has the smallest ionization energy. Helium has the largest ionization energy. So next, antimony right here, tellurium here, and tin here. So these three elements are in the same period, and as we know, across period from left to right, atomic size decrease, ionization energy increase. So tellurium has the highest ionization energy, and the tin has the smallest. C. Potassium, calcium, rubidium. So let's find them in the periodic table. Potassium here, calcium, and the rubidium here. And we know across period the ionization energy increase, and therefore potassium is smaller than calcium. And down a group, ionization energy decrease, and therefore potassium is greater than rubidium. And therefore our order is calcium is the largest, and then potassium, and then rubidium. So next, iodine. So iodine is here, and the xenon is here, and the cesium is here. So here, let's again compare, add one element. Let's add rubidium to compare all of them with rubidium. And across period, again, the ionization energy increase. So rubidium should be smaller than iodine, should be smaller than xenon. And down a group, ionization energy decrease. So rubidium should be greater than cesium. And therefore you can see cesium is the smallest, xenon is the largest. Core electrons are much harder to remove than outer shell electrons. Let's take beryllium as an example. Beryllium has 4 electrons. The electron configuration is 1s2, 2s2. To remove one of the electrons from outer shell electron, it takes 0.9 megajoule per mole energy, and this is the first ionization energy. And the resulting ion, cation, has electron configuration 1s2, 2s1. Okay, now this ion has a positive charge, so to remove another electron take more energy, and that's the second ionization energy, which is 1.76. So that's about twice the energy for the first ionization energy. So the resulting ion is a beryllium 2+, so 1s2. Now remember, this is the core electrons, the 2 electrons. And to remove another electron, it takes 14.85 megajoule per mole, and that's about 10 times of the second ionization energy. This table shows the successive ionization energies of the elements lithium through sodium. So we already talked about beryllium. So beryllium is here, and we showed that the first ionization energy is 0.9, and the second is twice of this, and the third ionization energy goes to almost 10 times, and that's because it starts to remove the core electrons. It takes much more energy than the outer shell electrons. Similarly, let's look at the first one, lithium. So lithium has 3 electrons, so 1s2, 2s1. So the first ionization energy to remove this electron is relatively easy, 0.52. Now after that, it becomes core electrons, and therefore it takes a lot more energy, 7.3. So second ionization energy for lithium jump to 7.3 megajoule per mole because it starts to removing the core electrons. Similarly, let's look at the boron. So boron ionizing, the electron configuration is 1s2, 2s2, 2p1. So to remove the first electron, and the ionization energy is 0.8. Okay, that's the 2p orbital. Now to next one is in the s orbital, so it takes more energy, so 3 times 0.8 because it goes to s orbital, take more energy, and then 3.66, so the second electron in s orbital. So after that, okay, it starts to remove the core electron. That's the ionization energy 4. Fourth ionization energy for boron jump to 25. Okay, so in general, you can see core electrons are much harder to remove. So for carbon, it jumped from 6.22 go to 37, and nitrogen from 9 to 53. Sample problem 8.5. Name the period 3 element with the following ionization energies and write its electron configuration. Now, from previous discussion, we know that a large increase in ionization energy indicates all valence electrons have been removed, and it starts to remove the core electrons. So if we look at the table from 1 to 2, it's a less than twice increase. 2 to 3, less than twice. 3 to 4, less than twice. 4 to 5, less than twice. 5 to 6, that's about 4 times. Okay, so that's the largest increase in ionization energy. So that indicates that up to 5th electron are all valence electrons. So this element has 5 valence electrons. Now it's period 3, so the electron configuration, the auto electron should be 3s2, 3p3. So 2 plus 3 give you 5 valence electrons. And this electron configuration should be phosphorus. If we look at periodic table, okay, you will find it's phosphorus, and Z is 15. So electron configuration up to level 2, so that's core electrons, and then valence electron, 3s2, 3p3. The third atomic property we want to discuss is electron affinity. Electron affinity is the energy change that occurs when 1 mole of electrons is added to 1 mole of gases, atoms, or ions. So ionization energy is the energy to remove an electron. Electron affinity is the energy change when electron is added. So one example is fluorine. Add 1 electron to form fluoride. So the energy change, this change is called ionization energy. And in this case is negative 328 kilojoule per mole. Okay, so that means, so if this is fluorine and this is fluoride, so the energy decrease give you a negative change. Okay, so a negative change means the energy decrease, and so it's exothermic, just like enthalpy. When enthalpy decrease, it's a enthalpy release heat. So this process go down energy, release heat. All right, and the lower energy of the product means it's more stable, because the added electron is attracted to the nucleus and therefore give you a negative delta E. Okay, so the larger this delta E means, the more easier the atom to attract the electron. So for example, a metal like sodium or lithium. Okay, lithium add the electron. All right, the delta E is much smaller. It's a negative 52. Okay, it's about negative 50 compared to 300 for fluorine. So the higher the electron affinity, in this case is the delta E. We look at the number, not the sign. Okay, the higher the electron affinity, the easier for the atom to attract electron and forms anions. So tend to form anions. And the lower electron affinity, so in this case smaller one, usually means that it doesn't like to add electron. Instead, it like to lose electron to form cations like metals, lithium. Okay, and the trends in electron affinity are not as regular as those for atomic size or ionization energy, as we'll see in the next slide. Here shows the electron affinities of the main group elements. So go down a group, we know the size increase. So electrons are further away from nucleus, and we know ionization energy decrease because electrons are further away. So it's easier to remove them, and you would expect it's harder to add the electron. So electron affinity should decrease. And that's what we see in group 1. So 72, 59, 52, 48, 46, 45. And then other groups are not as regular. For example, group 3, 26, and then increase to 42, and then decrease and decrease. Okay, and group 4 also 122 increase to 134, and then decrease, decrease, decrease. Okay, across a period, and we know the size decrease, the atomic size decrease, so it's harder to remove electron. Ionization energy increase, and you would expect the electron affinity decrease. Okay, so if we look at period 3, sodium 52, magnesium is not shown here. Aluminum decrease, so goes to aluminum decrease, and then increase to silicon 120, and then decrease again, and then increase. So in general, it has a trend to increase, but it's not as regular as atomic size and ionization energy. In summary, reactive nonmetals such as chlorine, fluorine have high ionization energy. Now, ionization energy is the energy to remove electron. These elements they don't lose electron easily, so it needs a lot of energy. So high ionization energy and high negative electron affinity. Electron affinity is the energy change to add electron. These elements likes to add electron. Okay, so when add electron, the energy becomes very low, so it releases a lot of energy, give high negative electron affinity. These elements attract electrons strongly, tend to form negative ions in ionic compounds. Reactive metals such as sodium, lithium, they have low ionization energy. They can easily lose electron, but they have slightly negative electron affinity, means adding electron is not favorable, and so they tend to form cations instead of anions. Now, noble gas such as argon, helium, they tend to neither lose electron nor gain electron, and therefore they have very high ionization energy, so they don't lose electron. And they have even positive electron affinity, so they don't attract electrons. In summary, in periodic table, go down a group, principal quantum number increase, electrons becomes further away from nucleus, and so the atomic size increase. And because electrons are further away, so it's easier to remove them, so ionization energy decrease down a group. And because they are further away, so adding electron is not favorable, and therefore electron affinity decrease or becomes less negative, but with many exceptions. Okay, now across a period, effective nuclear charge increase, so the atomic size decrease from left to right. Okay, because the atomic size decrease, so it's more attracted to nucleus, and therefore ionization energy increase from left to right, and adding electron becomes easier, so electron affinity should increase or becomes more negative, again with many exceptions. Electron configuration and effective nuclear charge not only determine atomic size, ionization energy, and electron affinity, but also affect many physical and chemical behaviors. One example is the metallic behavior. Metals are typically shiny solids with moderate high melting points. Metals are good conductors of heat and electricity and can easily be shaped. Metals tend to lose electrons and form cations. They are easily oxidized. Metals are generally strong reducing agents. Most metals form ionic oxide, which are basic in aqueous solution. As we go down a group, ionization energy decrease, metallic behavior increase. Let's take group 5 as an example. So here is group 5. So the first one is nitrogen, which is a gas. And the next one, phosphorus, is a soft non-metal solid. And the next two, arsenic and antimony, are metalloids. And the next one, bismuth, is a typical metal. Across the period from left to right, ionization energy increase and metallic behavior decrease. Elements to the left side are usually metals. They tend to lose electrons to form cations. Elements to the right side are usually non-metals. They tend to gain electrons to form anions. This picture shows group 5 and period 3 elements. So when we go down the group, metallic behavior increase. It starts with nitrogen as a gas, phosphorus as a non-metal solid, arsenic, antimony, metalloids, bismuth a typical metal. Across the period, metallic behavior decrease. So it starts with metallic sodium, magnesium. Aluminum is still a metal. Silicon is a metalloid. And then phosphorus becomes a nonmetal, and sulfur, nonmetal. Chlorine is a gas. Closely related to an element's tendency to lose or gain electron is its redox behavior, that is, whether it behaves as an oxidizing or reducing agent, and the associated changes in oxidation number. For most elements, the group number is the highest oxidation number. For example, magnesium group 2, so the oxidation number is +2. Aluminum group 3, oxidation number is +3. Sulfur group 6, so the highest oxidation number is +6. An example is SO3, and the oxidation number of sulfur in this compound is +6. Now, two exceptions, oxygen, fluorine. They are too difficult to lose 6 or 7 electrons in these two elements. Instead, for non-metals in general, the group number -8 is the lowest oxidation number. So, for example, nitrogen, group 5, so 5 - 8 is -3. So -3 is the lowest oxidation number for nitrogen. And in fact, for oxygen, 6 - 8 is -2. And this is almost always the oxidation number for oxygen, except in H2O2, which is -1. For fluorine, 7 - 8 is -1. So fluorine almost always oxidation number -1. Oxide of its main group metal is strongly basic. Calcium is a metal. Calcium oxide is basic. So this is because calcium oxide, add water, it forms calcium hydroxide, and which is a base. Oxide of a main group nonmetal is acidic. Phosphorus is a nonmetal, so P4O10 in aqueous solution is acidic, and this is because the oxide add water forms acids. We just showed that main group metals form ionic oxides which are basic in aqueous solution, and the main group of nonmetals form covalent oxides which are acidic in aqueous solution. Some metals and metalloids form amphoteric oxides, which can act both as acid or base in aqueous solution. So aluminum oxide can react with acid. Aluminum oxide can also react with base. Oxides become more basic down a group and more acidic across a period. So let's take group 5 as example. N2O5 is acidic. In water, it forms nitric acid. That's very strong acid. Tetraphosphorus pentaoxide in water forms phosphoric acid, which is a weak acid. And arsenic oxide in water is also weak acid. Antimony oxide becomes weak basic, and same is bismuth oxide becomes basic. Okay, so let's look at period 3. Sodium oxide, magnesium oxide are both basic. Okay, aluminum oxide becomes amphoteric, and silicon oxide becomes weak acid. Okay, so is the phosphor oxide. And then when we go to sulfur oxide, it becomes sulfuric acid and the perchloric acid, which are strong acidic. On the periodic table, elements on the left side tend to lose electron, and the elements on the right side tend to gain electron, so that they attain a field auto level. The resulting ion will have a noble gas electron configuration and is said to be isoelectronic with the noble gas. So let's use sodium as the example. Sodium is on the left side of the periodic table, and this is the electron configuration, which has one more electron than neon. So after losing this electron, it has the same electron configuration as neon, and so we can say sodium ion is isoelectronic with neon. Okay, similarly, bromine is on the right side of the periodic table, one less electron than krypton. To attain the same electron configuration of a noble gas, here is a krypton, it needs to gain electron. So after gaining one electron, now the ion has same electron configuration of krypton. So bromide is isoelectronic with krypton. This diagram shows the main group elements whose ions have noble gas electron configuration. So these are noble gas elements, and let's use neon as an example. And neon is on second period, and oxygen has 2 electrons less than neon, so it will gain 2 electrons to be isoelectronic with neon. Fluorine, 1 less electron than neon, so it gains 1 electron to become fluoride, which is isoelectronic with neon. Sodium, magnesium are on the third row, so sodium has 1 more electron than neon. It loses 1 electron to become sodium cation, which is isoelectronic with neon, and magnesium loses 2 electrons to become isoelectronic with neon. Not all main group elements form ions that are isoelectronic with noble gas. Many of the metals in group 3, 4, 5, they form cations with 2 different stable configurations. Let's use tin as an example. Tin belongs to period 5. The previous noble gas is krypton, so we can write the electron configuration of tin as bracket krypton, and then 2 electrons in the 5s orbital, so that's these 2 electrons, and 10 electrons in the 4d orbitals. So here are the d orbital electrons, and then 2 electrons in 5p orbital. Okay, now by losing 4 electrons, okay, 2 from 5s orbital, 2 from 5p orbital, it gives a cation with d orbital 4, okay, 4d10 electrons. And this is called a pseudo noble gas configuration. It's attained when metal at an empty its highest energy level, which in this case is 5s 5p. Okay, so the result is a n-1 d orbital 4. Okay, it's a field n-1, which is 10 electrons. Okay, so that's a stable configuration called the pseudo noble gas configuration. On the other hand, more commonly, tin lose 2 electrons from the p orbital, so that s orbital, okay, is 4, d orbital is also 4, and this is called inert pair configuration. So tin can lose 4 electrons, can also lose 2 electrons. Sample problem 8.6. Using condensed electron configurations, write reactions for the formation of the common ions of the following elements. So first we need to identify the position of each element on the periodic table, and recall that ions of group 1 to 16, 17, or the left side and the right side are usually isoelectronic with the nearest noble gas. And the metals in group 3, group 5 can form cations with two different stable configurations. Okay, one is losing NSNP, one is just lose NP electrons. A. Iodine, atomic number 53 in the periodic table is right here, which has one less electron than xenon. So it should gain one electron to form iodide. And the previous noble gas is krypton. So we can write electron configuration as bracket krypton, and then start to fill electron in 5s orbital, so 5s2, 4d10, and then 5p5. Okay, so that's the electron configuration. By gaining one electron, it gives you iodide with same electron configuration as xenon. Okay, next one, potassium 19. So here is potassium. So potassium is one electron more than argon. So it should lose one electron to be isoelectronic with argon. And the electron configuration is brackets argon and then 4s1. Okay, one electron more than argon. So by losing one electron, it forms potassium cation with argon electron configuration. Okay, next one, indium, atomic number 49. So it's right here. And this is group 3, as we shown before. Group 3 will form cations with two different stable configurations. And so first we write electron configuration again, start with krypton, and then 5s2, 4d10, all right, and then 5p, one electron right here. Okay, one electron in p orbital. So one way to achieve a stable configuration is to lose the highest energy levels, which is 5s, 5p, and that will give you indium 3+, okay, because it loses 3 electrons, and so it has a 4d10, okay. The other way is just lose the p orbital, so that it has 5s2, okay, s orbital is 4, d orbital is 4, and so this is indium 1+. When an orbital holds 2 electrons with opposite spin, it's called paired. And when an orbital has only 1 electron, it's called unpaired. A species with 1 or more unpaired electrons exhibit peromagnetism. That is, it is attracted by a magnetic field. And this is because a spin serves as a magnet. So when a orbital field holds 2 opposing spin, the 2 magnets, small magnets, cancel each other. And therefore, a species with all its electrons paired exhibit diamagnetism, and that is, it is not attracted and is slightly repelled by a magnetic field. This shows how magnetic behavior of a sample is measured. A balance, one side has an object with the same mass as a sample, and the sample is inserted inside a magnetic field. When the sample is diamagnetic, that means all electrons are paired. The balance does not move, so the apparent mass of diamagnetic substance is unaffected by a magnetic field. On the other hand, if the sample is paramagnetic, and that means the sample contains at least one orbital with an unpaired electron, the sample is attracted by the magnetic field. The apparent mass of a paramagnetic substance increase as it is attracted by the magnetic field. Magnetic behavior can provide evidence for the electron configuration of a given ion. For example, titanium-22 has electron configuration of the auto electrons are 4s2, 3d2. The two electrons in 3d orbital are unpaired. Titanium can lose two electrons to form titanium-2+. The question is, does titanium lose two electrons from 4s orbital or from 3d orbital? If it loses two electrons from 3d orbital, then the cation should have two electrons that are paired, so it should be diamagnetic. Okay. On the other hand, if it loses two electrons from the s orbital, then it has two electrons in the d orbital that are unpaired, so it should be paramagnetic. Experiments show that titanium-2+ is paramagnetic. Okay, so that provides evidence that 4s electrons are lost before 3d electron. So here is the correct electron configuration for titanium-2+. Sample problem 8.7. Use condensed electron configurations to write the reactions for the formation of each transition metal ion and predict whether the ion is paramagnetic or diamagnetic. So first, write the condensed electron configuration for each atom and record the irregularity for chromium. Remove electrons beginning with ns electrons and determine if there are any unpaired electrons. In A, manganese. So here is the manganese. Okay, the previous noble gas is argon. So electron configuration is argon brackets and 4s2. So this is 2 electrons, and 3d5. So these are 5 electrons. All right. To make manganese 2+, this atom should lose 2 electrons, and that's the s orbital. So it should lose s orbital first before d orbital, and that gives you electron configuration 3d5. Okay, remember there are 5 d orbitals, so the 5 electrons should enter to each of the 5 orbitals according to Hund's rule, and therefore these electrons are unpaired, 5 unpaired electrons, and therefore manganese 2+ should be paramagnetic. Next one is chromium. Chromium is right here, and looking at the periodic table, okay, we may write argon bracket and then 4s2, 3d4. Okay, you have 4 electrons, okay, in d orbitals. Now remember, orbitals, field orbitals or half-field orbitals are exceptionally stable. So chromium is one of those elements that show irregularity, and that means it can move electron from s orbital to the d orbital, so that the s orbital is half-field and the d orbital is also half-field. 5 electron is half-field, 10 electron is 4. So both s and d are half-field. It's stable. Okay, so that's the electron configuration for chromium. To form chromium 3+, it first loses the electron from s and then 2 from the d, and so it gets 3d3. Okay, 3 electrons in the 3d. So again, there are 3 orbitals or 5 orbitals, only 3 electrons. Each enters 3 different orbitals. They are parallel spin, and therefore it's paramagnetic. Okay, next one is mercury. So mercury is right here, and the previous noble gas is xenon. So electron configuration should be xenon brackets 6s2 electrons, and then between 6s and 5d here there are 14 f orbital electrons, so 4f14, and then 5d10. So these are 10 electrons, 5d10. Okay, to form Mercury 2+, it needs to lose 2 electrons, and that's from s orbital. And so the electron configuration for Mercury 2+ is xenon bracket 4f14, 5d10. So because both F and D are 10 electrons and 14 electrons, so all the electrons are paired, and this ion is diamagnetic. How is ionic size compared to atomic size? Well, cations are smaller than their parent atoms. For example, sodium cation is smaller than sodium. And this is because one electron is removed from sodium, so size becomes smaller. Anions are larger. For example, fluoride is greater than fluorine. This is because one electron is added to fluorine, so size becomes bigger. Cation size decreases as charge increases. So when ion loses 2 electrons, the size becomes smaller than parent ion itself. When ion loses 3 electrons, it becomes even smaller. Here shows ionic versus atomic radii. Lithium atomic size 152, cation 76, cation is bigger. Fluorine 72, the anion 133, anion is larger. Now let's look at the trend. Okay, down a group, principal number increase, atomic size increase. So lithium 152, sodium 186, potassium 227, rubidium 248. So atomic size increase. What about the ionic size? Okay, lithium 76, sodium 102, potassium 138, rubidium 152. So ionic size radius also increases down a group as n increases. Across a period, the pattern is complex. Let's look at period 3. Okay, from left to right, effective nuclear charge increase and atomic size decrease. And sodium 186, magnesium 160, aluminum 143, phosphorus 110, sulfur 103, chlorine 100. So from left to right, atomic size decrease and the trend is consistent. What about the ionic size? Sodium cation 102, magnesium 2+, 72, aluminum 54. So cations also decrease the size from left to right. Okay, anion phosphorus 3 negative, 212, sulfur 2 minus, 184, and chloride 181. So from left to right, the anions also decrease in size. However, between cation and anion, there's a big increase. So aluminum cation size radius 54, phosphorus anion radius 212. So anions in general are larger than cations in a same period. We can also compare ionic sizes in an isoelectronic series. An isoelectronic series is a series of ions that have the same electron configuration. So when fluorine gains an electron, it becomes same electron configuration of neon. Similarly, oxygen gains 2 electrons to become isoelectronic with neon. Nitrogen gains 3 electrons to become isoelectronic with neon. Sodium has 1 more electron, so it loses an electron, and sodium cation is isoelectronic with neon. Similarly, magnesium 2+, aluminum 3+, these are all isoelectronic with neon. However, these ions have different protons. Oxygen has one more proton than nitrogen. Fluorine has one more than oxygen. Sodium has one more than fluorine. So when we go from nitrogen to oxygen to fluorine, to sodium to magnesium to aluminum, these cations or anions, they all have same electron configuration but different protons. Protons increase. When number of protons increase, electron outside the electron is more attracted to the nucleus, and therefore the radius are expected to decrease. Okay, that's what we see here in the isoelectronic series. So nitrogen 3 minus radius 146, oxygen 2 negative radius 140, so decrease. Fluoride 133, and then go to sodium cation 102, becomes smaller. Magnesium 2+, 72, aluminum 54. Okay, so from nitrogen to oxygen to fluorine to sodium to magnesium to aluminum, these isoelectronic series ions size decrease. Okay, we can use ions, the charge, to show the series. 3 negative for nitrogen, 2 negative for oxygen, 1 negative for fluorine. Okay, so the size decrease to cation, 1 plus cation, 2 plus cation, 3 plus cation. Sample problem 8.8. Rank each set of ions in order of decreasing size and explain your ranking. So we'll find the positions of each element on the periodic table and apply the trends for ionic size. A. Calcium, strontium, magnesium. Calcium is here, magnesium, strontium. So these three cations are all in the same group, group 2. And therefore we know down a group, principal number increase, the radius increase for both atomic size and ionic size. And therefore we have strontium the largest, and then calcium, and then magnesium. Okay, next, potassium. So potassium is here, and sulfur is here, and the chloride here. So we can see these three ions are an isoelectronic series. They all have electron configuration same as argon. Okay, so we know the size goes from sulfur to chloride to potassium to calcium. So here is the answer. All right. Next one, gold plus, gold 3+. Okay, so the higher the charge for cation, the smaller the size. And so gold 1+ is greater than gold 3+.